Okay, so at the previous lecture we introduced C-star algebras, and we almost approached a fundamental result about them, namely the first Gelfand-Nymark theorem. So to begin with, let's recall some important theorems on C-star algebras, which were proved at the previous lecture. So A is a unital C-star algebra, unital C-star algebra. The first fact, which was proved at the previous lecture, is that for any normal element, A in our algebra, the normal way equals the spectral radius. So let's recall that in the general case, the spectral radius is less than or equal to the norm. But for normal elements of C-star algebras, we have an exact equality. And the second important fact is that for each self-adjoint element, in our algebra, the spectrum of A is real. And as a corollary of this, we proved that all characters of A are star characters. That is, they preserve the involution. Okay, now before we formulate and prove the Gelfand-Nymark theorem, let's recall a fundamental result from general topology, namely the Stone-Weierstrass theorem. Suppose that X is a compact Hausdorff topological space. And suppose that A is a star subalgebra of the algebra of continuous functions on X. A star subalgebra which contains the identity of C of X, that is, contains the function which is identically 1. And suppose that A separates the points. Suppose that A separates the points of X. Then A is dense in C of X. So this is a useful result in general topology that we will need in our proof of the Gelfand-Nymark theorem. I'd like to stress once again that, sometimes in courses of calculus or in courses of general topology, you can meet a real version of this theorem, which works with algebras over the real numbers. So over the real numbers, A is just a subalgebra, not a star subalgebra, but just a subalgebra of C of X, which contains the identity and which separates the points. And in this case, it is dense in the algebra of real-valued continuous functions on X. But since we are dealing with complex algebras, it's essential to require here that A is a star subalgebra. Otherwise, we can find rather simple counterexamples. Okay, now we can prove the Gelfand-Nymark theorem. Suppose that A is a commutative unital C-star algebra. Then the Gelfand transform of A, which is a homomorphism from A to the algebra of continuous functions on the maximal spectrum. So this map is defined for each commutative unital Banach algebra. And the theorem states that if A is a commutative unital C-star algebra, then this homomorphism is an isometric star isomorphism. An isometric star isomorphism. Okay, so to prove the result, let's first observe that gamma is a star homomorphism. So we take an arbitrary element in A. We apply gamma to A star and evaluate at the point X. So what is this? By the definition of the Gelfand transform, this is X applied to A star. So here we identify a point in the maximal spectrum with the respective character of A. Okay, now we look here. We know that all characters of A are star characters. So little x preserves the involution. And so this is X of A complex conjugate. But this is nothing but gamma A of X complex conjugate. And since the involution in the algebra of continuous functions is the complex conjugation, this shows that gamma is a star homomorphism. Okay, let's now look at the image of gamma. The image of a star homomorphism is always a star subalgebra. The image of gamma is a star subalgebra in the algebra of continuous functions on the spectrum. And it is easily seen that this subalgebra satisfies the conditions of the Stone-Weierstrass theorem. Well, it's a star subalgebra. It contains the function which is identically 1, because gamma is a unital homomorphism. And it clearly separates the points by the very definition of the Gelfand transform. If you have two different points in here, that is, two different characters, then they are different on a certain element of A, which means that the respective element in the image of gamma separates the respective points. So we apply the Stone-Weierstrass theorem, and we conclude that the image of gamma is dense in the algebra of continuous functions. Now to complete the proof, we have to show that the gamma is isometric. This will be the end of the story, because if it shows that it is isometric, well, an isometric operator between Banach spaces has closed image, and since the image is dense, this will show, this will imply that gamma is an isometric isomorphism. Okay, we start with the self-adjoint element. Let's recall that ASA is our short notation for the set of all self-adjoint elements. So we take a self-adjoint element of A. So what is the norm of gamma of A? Well, it is one of the basic properties of the Gelfand transform, which holds for each commutative unital Banach algebra, that the norm of the Gelfand transform is equal to the spectral radius of A. So this holds for each commutative unital Banach algebra. But now we recall that A is a C-star algebra, and our element is self-adjoint. And we apply this equality. For a self-adjoint element, the spectral radius equals the norm. And so we see that gamma is isometric on the set of self-adjoint elements. And now we extend the same result to an arbitrary element in our algebra by using the C-star identity. Namely, the norm of gamma of A squared is the norm of gamma of A star gamma of A, because the algebra of continuous functions is a C-star algebra. We can now write this in the following form. This is the norm of gamma applied to A star A, because gamma is a star homomorphism. But A star A is self-adjoint. This element is self-adjoint. And we already know that for self-adjoint elements we have this equality. So this is equal to the norm of A star A. And finally, since A is a C star algebra, we see that by the C star axiom, this is the norm of A squared. So this chain of equalities shows that gamma is isometric. And this completes the proof. Надо было так стирать. Бог с ним. Okay, now let me say a few words about a category theoretic interpretation of the Gelfand-Naimark theorem. Well, if you don't like, those of you who don't like abstract nonsense may easily skip this part of the lecture. Close your eyes and relax. Well, this part of the lecture is not essential for the rest of the course, but I believe it is essential for understanding mathematics in general. So let's consider two categories. The first category will be denoted like this, comp. The objects of this category are compact Hausdorff topological spaces. And the morphisms are continuous maps. And the second category will be denoted like this, CUC star. Here the objects are commutative unital C star algebras. And the morphisms are unital star homomorphisms. Which are always continuous, which was proved some time ago that each star homomorphism from a Banach star algebra to a C star algebra is continuous. Okay, so these are our categories, and let's now consider two functors, two contravariant functors. The first functor already implicitly appeared at the previous lecture. We denote it by C. It acts from the category of compact spaces to the category of commutative unital C star algebras as follows. It takes each compact Hausdorff space X to the algebra of continuous functions on X. So this is the action on objects. And the action of morphisms looks as follows. You have a continuous map f from x to y. Then our functor takes this map to the induced homomorphism f dot from C of y to C of x, which takes each continuous function g on y with g composed with f. Clearly, this is a unital star homomorphism. So this is our first functor. And the second functor acts in the opposite direction. It will be denoted by max. It acts from CUC star to the category of compact spaces as follows. It takes each commutative unit of C-star algebra to its maximal spectrum, which is a compact Hausdorff space. So this is the action on objects. And now the action on morphisms looks as follows. If phi is a star homomorphism from A to B, then the respective map, phi star, from the spectrum of B to the spectrum of A acts as follows. We, again, interpret maximal ideals as characters. So if chi is a character of B, we just compose chi and phi, and we get a character of A. Why is it continuous? It is continuous because phi star is the restriction of the respective dual operator, phi star, between the weak star dual spaces. So we recall that the Gelfand topology on the maximal spectrum is the restriction of the weak star topology. And we know that the dual of any continuous map between locally convex spaces is continuous for the weak star topologies. So phi star is the restriction of this dual map, which is known to be continuous. Okay. So we have two functors. Let's draw a picture. We have two functors which act in the opposite direction. This is C, and this is max. So let's make these functors covariant by replacing the category of compact spaces by the opposite category, the dual category, with the same objects and with the arrows reversed. I claim that these two functors are equivalences of categories. So this is a category theoretic form of the Gelfand-Naimark theorem. And more exactly, these functors are quasi-inverse to each other in the sense that if we compose them, then the composition will be isomorphic to the identity functor. The proof is actually a reduction to the Gelfand-Naimark theorem, modulo some very elementary computations. Namely, let's recall that if X is a compact Hausdorff space, then we have a canonical homomorphism epsilon x, between X and the maximal spectrum of C of X. So this homomorphism was constructed at the beginning of the previous lecture, and it takes each point in here to the evaluation character on C of X. So we prove that this is a homomorphism. But if we now consider the collection of all such homomorphisms for all compact spaces, then it is very easy to show that this family is a natural transformation. It's a natural transformation from the identity functor to the composition of max and C. And this is a simple exercise. Basically, we have to show that this suitable diagram commutes. And the other way around, if we now start with a commutative unit of C-star algebra A, a commutative unit of C-star algebra, then we consider the Gelfand transform of A So the Gelfand dynamic theorem states that it is an isometric star isomorphism. But if we consider all such Gelfand transforms, then again it is elementary to check that this is a natural transformation. Natural transformation from the identity functor to C composed with max. And this completes the proof. This means exactly that C and max are quasi-inverse equivalences of categories. So the meaning of the Gelfand dynamic theorem is that it gives us a perfect example of a complete duality between algebra and geometry, or maybe between topology and algebra and topology. So it establishes a duality between pure topological category of compact spaces and the category of commutative unital sister algebras, which is not entirely algebraic, but is essentially algebraic. By the way, there is another result in mathematics of the same form, namely a category theoretic form of Hilbert's Neustadt and Satz states that we have a duality between the category of affine algebraic varieties over the complex numbers and commutative finitely generated algebras without nilpotence. And all results of this form lead us directly to non-commutative geometry. Actually, there are many different forms of non-commutative geometry. So the fundamental principle of those, of the part of non-commutative geometry which is related to functional analysis, is that it is very useful to consider an arbitrary unital C-star algebra, not necessarily commutative unital C-star algebra, as the algebra of continuous functions on a non-commutative compact topological space. That is, on a space which doesn't actually exist. This point of view may seem quite paradoxical at the first glance, but in fact it indeed leads to a very deep and beautiful theory with many interesting applications. And quite often it turns out that many topological constructions, after we translate them into the dual language, into the language of C-star algebras, make perfect sense for non-commutative C-star algebras as well. And a good example of such translation is K-theory. So it turns out that topological K-theory, which deals with vector bundles over compact spaces, is completely embedded into K-theory of C-star algebras. Okay, let me now make some short remarks on the non-unital case. Remarks on the non-unital case. In our course, we are interested mostly in unital algebras, and this is sufficient for our applications to spectral theory. But in fact, there are many reasons to consider non-unital algebras as well. And this is an essential difference between pure algebra and functional analysis. So in pure algebra, it is absolutely customary to consider only unital algebras and rings with identity. But in functional analysis, this is not the case. And there are many reasons for that. On the one hand, there are many natural examples of non-unital Banach algebras and non-unital C-star algebras, such as, for example, algebras of compact operators, or the group C-star algebra of a non-discrete locally compact group. And such algebras naturally arise in various applications to, say, representation theory, harmonic analysis, or quantum group theory. And on the other hand, there are several important constructions in C-star algebra theory, such as stabilizations, suspensions, and so on, which play an essential role in K-theory and which always produce non-unital algebras. So there are many reasons to consider non-unital algebras, and because of that, let me just say a few words about the Gelfand theory for non-unital Banach algebras. It turns out that in the non-unital case, we have to redefine the maximal spectrum. So the collection of all maximal ideals is no longer relevant. Instead of that, we must consider only modular maximal ideals. Maximal modular ideals. An ideal in a commutative algebra is called modular if the quotient is unital. So if we consider maximal modular ideals, then it turns out that many results that we proved for maximal ideals in unital Banach algebras hold for maximal modular ideals in arbitrary commutative, not necessarily unital Banach algebras. In particular, we still have a canonical bijection between the character space, the set of all non-zero characters, and the maximal spectrum, the set of all maximal modular ideals, which takes each character to its kernel. Also, it is true that all maximal modular ideals of a Banach algebra are closed. In the unital case, we know that the maximal spectrum is a compact Hausdorff space. In the non-unital case, we introduce the topology in exactly the same way. The difference is that the space is no longer compact, but it is locally compact. Locally compact Hausdorff topological space. The Gelfand transform of each element in our algebra is defined in exactly the same way, and it is still a continuous function on the maximal spectrum. But now we can say more. It is not only continuous, but it also vanishes at infinity. The algebra of continuous functions which vanish at infinity is denoted by C0. And this vanishing at infinity condition means that for each positive epsilon, we can always find a compact subset of our space. So X is the maximal spectrum, such that our function is less than epsilon outside K. This means that a hat vanishes at infinity. So the Gelfand transform becomes a homomorphism from A to the algebra C0 of continuous vanishing at infinity functions on the maximal spectrum. The properties of this map are similar to the unital case. And the Gelfand-Narmek theorem, the commutative Gelfand-Narmek theorem, states that this map is an isometric star isomorphism for each commutative C-star algebra. If A is a commutative C-star algebra. So basically, this is the main difference between the unital case and the non-unital case. Okay, now our next goal is to discuss the continuous functional calculus in C-star algebras. Suppose that we have a unital Banach star algebra, A, and suppose that little a is a normal element over here. Roughly, our goal will be to give a precise meaning to the expression f of A, where f is a complex-valued function, complex-valued continuous function, defined on a suitable compact subset K of the complex plane. of course, if f is a polynomial, then f of a is already defined. And probably you also know what f of a is in the case where f is the exponential function. So you take the exponent, you decompose it into a power series, and you substitute a to this power series. So our goal will be to extend this expression to more general continuous functions, which are not necessarily given by power series. Okay, so we start with a normal element. Suppose that K is a compact subset of the complex plane. And let little t denote the inclusion map of K into the complex plane. T of lambda is lambda. And we give the following definition. A continuous functional calculus for A on the set K is a continuous unital star homomorphism gamma A from the algebra of continuous functions from K to A such that gamma takes this little t, the coordinate on K, to the element A. By the way, let me explain the terminology. The word continuous here refers not to the continuity of gamma, but to the fact that gamma is defined on the algebra of continuous functions. So if I replace, for example, the algebra of continuous functions by the algebra of holomorphic functions, then we speak about the holomorphic functional calculus. But we will be interested in the continuous functional calculus. Well, first of all, let's observe that if such a homomorphism exists, then it is unique. Of the following proposition, if gamma exists, then it is unique. To prove this result, we just observe that by the Stone-Weierstrass theorem, the subalgebra of C of K, the star subalgebra of C of K generated by the function which is identically 1, the function t, and the complex conjugate t bar, satisfies the conditions of the Stone-Weierstrass theorem. So it is dense. It's dense in C of K. It's a star subalgebra which contains the identity, and clearly it separates the points. So it is dense, and this condition shows that gamma is uniquely determined on this subalgebra. So if it can be extended to C of K by continuity, then this extension is unique. Okay, now how about the existence of the continuous functional calculus? First of all, I recommend you the following exercise. Construct a unital Banach star algebra and a normal element for which the continuous functional calculus never exists. whatever k is. So there is no compact set for which there is continuous functional calculus. Okay, but it turns out that for C-star algebras, everything is okay. So we start with a simple necessary condition for the existence of functional calculus, which, by the way, works for all Banach-star algebras. So if gamma A exists, then the compact set K contains the spectrum. This is a necessary condition for the existence of the functional calculus. The proof is very easy. The spectrum of A, so A is gamma of T by assumption. A is gamma of T. And gamma is a unital homomorphism. A unital homomorphism doesn't increase the spectrum, so this is an equality, but this is contained in the spectrum of T in C of K. But the spectrum of a continuous function is just the range. But since T is the inclusion map, we get that this is K. And we see that the spectrum is contained in K. So it turns out that if A is a C-star algebra, then this condition is also sufficient for the existence of a functional calculus. Before we prove this, let's introduce some useful notation. Suppose that A is a C-star algebra, and let S be a subset of A. We define the C-star subalgebra of A generated by S, and we write the symbol. We define it to be the intersection of all C-star subalgebras containing S. The intersection of all B, where B is a C-star subalgebra of A, a closed star subalgebra containing S. Well, since the intersection of any family of C-star subalgebras is clearly a C-star subalgebra, we see that this is the smallest C-star subalgebra containing S. And we call it the C-star subalgebra generated by S. Let's observe the following. It's not a proposition, this is just an observation. First of all, we can describe this subalgebra explicitly as follows. So we take the closure of the linear span of all words A1 to AN, of all finite products of arbitrary length, where each symbol here sits either in S or in S adjoint. Well, indeed, it's easy to see that the closure of this linear span is indeed a C-star subalgebra, and clearly it is the smallest C-star subalgebra containing S. Let's now look at a special case. So this is the first observation. Let's now look at a special case. Suppose that A is unital. Suppose that A is unital. And little a is a normal element. Then the C-star subalgebra of A generated by A, and the identity, is the closure of the set of all polynomials in A and A star. So here P runs over the algebra of polynomials into variables. So we substitute A and A star in this P, and we take a closure. This is a special case of the previous formula, because if we consider such a word where each AI is either A or A star, well, A and A star commute, so we can make this word into a monomial in A and A star, and the closure of the linear span is just the closure of the set of all polynomials in A and in A star. And another, even more special case is the case where A is self-adjoint. In particular, if A is self-adjoint, then the C star subalgebra of A, generated by little a and the identity, is the closure of the set of all polynomials f of A, where f runs over the polynomial algebra in one variable. Okay, let's now come back to the functional calculus. So we have the following result. Suppose that A is a unital C star algebra, and little a is a normal element. Then, for each compact subset K of the complex plane, such that K contains the spectrum, there exists a unique continuous functional calculus for A on K. So we already know that it is unique. Now let's show that it always exists. Moreover, if K is exactly the spectrum of A, then we can say more. In this case, gamma A is an isometric star isomorphism. An isometric star isomorphism of C of spectrum onto the C star subalgebra of A generated by little a and the identity onto this subalgebra. Okay, let's now prove this result. First of all, we observe that we can reduce everything to the case where K is exactly the spectrum. So we may assume from the very beginning that K is exactly the spectrum. Well, indeed, if K contains the spectrum, then we can look at the following picture. We can first take the restriction map from C of K onto the algebra of continuous functions on the spectrum, the restriction map. And clearly, this is a unital star homomorphism. So if we have already constructed the functional calculus on this algebra, then we can simply compose these two arrows to get a functional calculus on C of K. So everything is reduced to the existence of this homomorphism, to the functional calculus on the spectrum. So from now on, we assume that K is exactly the spectrum. So let's take this C-star subalgebra generated by little a and the identity element, and let's denote it by B. So let B be the C-star subalgebra of A generated by little a and the identity. We observe that this is a commutative C-star algebra. B is a commutative unital C-star algebra. It is commutative because A is normal. And we have this explicit description for this subalgebra. Also, let's call the spectral invariance result, which was proved at the previous lecture. Spectral invariance. The spectrum of our element little a, taken with respect to the algebra A, equals the spectrum with respect to the smaller algebra B. This is true for each unital C-star algebra and for each unital C-star subalgebra A. So we have this equality. Okay, let's now look at the following map, little phi. So phi takes the maximal spectrum of B to sigma of A by the following formula. So basically, this is just the Gelfand transform of the element little a, considered as an element of B. But we consider this Gelfand transform as a map from the maximal spectrum to sigma of A. And it follows from the properties of the Gelfand transform that phi is surjective. Let's see the general properties of the Gelfand transform. Well, it was one of the general properties of the Gelfand transform that the range of a hat is precisely sigma of A. So we just look at a hat as a map from the maximal spectrum onto the spectrum of A. I claim that phi is actually is a homeomorphism. That shows that phi is a homeomorphism. Well, why is it surjective? Suppose we have 2 points in the spectrum of B, x1 and x2. And suppose the phi of x1 equals phi of x2. So in other words, this means that, if we recall the definition of the Gelfand transform, this means that x1 of A equals x2 of A. Well, now, since x1 and x2 are star characters, all characters of a C-star algebra are star characters, this implies that x1 of a star is equal to x2 on A star. So they are the same on A. They are the same on A star. And let's now look here. So clearly they're the same on each polynomial in A and in A star. And this implies that x1 equals x2. Because B is generated by A and the identity. So phi is bijective. Phi is bijective. And since it is also continuous, the Gelfand transform is a continuous function, and since this is a compact space, we conclude that phi is a homeomorphism. So the compactness argument implies that phi is a homeomorphism. So this is exactly the place where two different meanings of the word spectrum coincide. The maximal spectrum of B and the spectrum of its element are homeomorphic. Okay, let's now use this fact for our construction of functional calculus. So we take the algebra of continuous functions on sigma of A. So we have a unital star, an isometric star isomorphism phi dot between this algebra and the algebra of continuous functions on the maximal spectrum, max B. So this is the isomorphism induced by phi. This algebra is homomorphic, is isometrically star isomorphic to B by means of the inverse of the Gelfand transform, gamma B inverse. So here we use the Gelfand-Naimark theorem. And B is contained in A. So we have the inclusion map here. Now we just compose these arrows. And we get an isometric star homomorphism from here to here, whose image is exactly B by construction. So now to complete the proof, it's enough to show that gamma takes T to A. That is, gamma satisfies the definition of the functional calculus. So we want to show that gamma of T equals A. Why is it so? Well, to show that this is the case, we have to, we'll look here. So we have to show that gamma B inverse of phi dot of A, or phi dot of T, equals A. Why is it so? Well, we apply gamma to both sides. So this is equivalent to the following equality, phi dot of T equals A hat. But what is phi dot of T? This is the composition of T and phi. And T is just the inclusion map of sigma of A into the complex plane. So if we now recall the definition of phi, we see that this equality is true by the definition of phi. Okay, so this equality holds, and so gamma is indeed a continuous functional calculus for our element little a on the spectrum. Excuse me, what extent? Which functional calculus? In Russian. Непрерывное функциональное исчисление. Непрерывное функциональное исчисление. Okay, so let's now observe the following. First of all, if f is a polynomial in one variable, then we can consider the restriction of f to k. Of course, this will be a continuous function. And after we apply the functional calculus, what we get is just f of a. For the simple reason that gamma is a homomorphism. So it takes T to A. So since it's a homomorphism, it takes each polynomial f to f of a. And more generally, if we have a polynomial f in two variables, x and y, let's denote by f tilde the following function. F tilde of z is f applied to z and z complex conjugate. So this is a polynomial in the coordinate z and in the complex conjugate coordinate. And we observe that if we take f tilde and restrict it to k, and then apply gamma, what we get is just f applied to A and A star. Or briefly, f tilde applied to A. And this is true because gamma is a star homomorphism. So it takes the bar to A star. So these two observations imply they justify the following notation. So for each continuous function f on K, where K is a compact subset containing the spectrum, we denote by f of A gamma of f. So instead of writing gamma of f, we write f of A. And we say that this is f evaluated at our element. This is reasonable because of this observation. So if f is a polynomial, then we get just the polynomial applied to f in the usual sense. Okay, let's now look at some basic properties of the functional calculus. The first property is the spectral mapping theorem. Spectral mapping theorem. In Russian, теорема об отображении спектра. Spectral mapping theorem. The formula is very easy. So I claim that for each continuous function f on the spectrum of A, we have the following equality. The spectrum of f of A equals f of sigma of A. That is the image of the spectrum under f. So it's a standard fact that this formula is true for polynomials in each unital algebra. In particular, this was proved at the lectures in the previous term. Now we have to show that this formula is true for each continuous function, provided that little a is a normal element of a C-star algebra. Okay, so what is sigma of f of A? Well, f of A is our notation for gamma of f. Now let's recall that gamma is an isomorphism onto the C-star subalgebra generated by little a and the identity. And by the spectral invariance, we can replace here A by this subalgebra. So here B is the C-star subalgebra generated by A and the identity. So this is true by the spectral invariance. But since now gamma is an isomorphism of the algebra of continuous functions onto B, this is equal to the spectrum of f in the algebra of continuous functions on sigma of A. But again, we know that the spectrum of a continuous function is just the range. And that's it. Another useful property of the functional calculus is the so-called superposition property. Again, as before, we assume that little a is a normal element of a unital C-star algebra. Suppose that f is a continuous function on the spectrum of A. And suppose that g is a continuous function on the spectrum of f of A. So f of A is also easily seen to be a normal element. So we can apply g to f of A. So this is well defined. I claim that this is nothing but the composition of G and F applied to A. By the way, let's observe that this superposition is well defined by the spectral mapping theorem. So the spectral mapping theorem states exactly that the range of F is the domain of G. So we can compose them. The proof is very easy. We observe the following. We look at the following map, just gamma, from the algebra of continuous functions on the spectrum of f of A, which takes G to the following element. Well, it's easy to see that gamma is a unital star homomorphism. Gamma is a unital star homomorphism. So the uniqueness of the functional calculus implies that gamma is the functional calculus of the element gamma of t. But gamma of t is, what is gamma of t? Gamma of t is just f of A. So by the uniqueness of the functional calculus, we conclude that gamma is the functional calculus of the element f of A. And this is exactly what we wanted to show. So this expression is equal to this one. Okay. Well, a little possible problem with the functional calculus is that it is not given by an explicit formula. And the reason is more or less immediate from the proof of our theorem. So the construction of the functional calculus involves the inverse of the Gelfand transform, which is quite unexplicit. So we know that it exists, but the inverse of the Gelfand transform is not given by an explicit formula. However, in many concrete cases, it turns out that an explicit formula for the functional calculus exists. And here are two illustrations. Exercise 1. Suppose that A is the algebra of continuous functions on a compact Hausdorff topological space, X. In this case, for each element in our algebra and for each continuous function f on the spectrum, the functional calculus is just the composition of f and A. And one more exercise. Similar to exercise 1, but a little bit more interesting. Suppose now that we have a measure space, a sigma finite measure space, x mu, and we take an essentially bounded measurable function phi on this space. Now let's consider the multiplication operator. Let's consider the multiplication operator, m phi, on the big O2 space. This is the multiplication operator, which takes each L2 function psi to the product of phi and psi. This is easily seen to be a normal operator. So the joint operator is the multiplication by the complex conjugate function. And clearly, two such operators commute. So it's a normal operator. So we can construct a continuous functional calculus. So the exercise is to show that for each continuous function f on the spectrum of this operator, f applied to this operator is again the multiplication operator by the composition of f and phi. I'd like to stress that this exercise involves giving a precise meaning to this expression. So in particular, try to understand what is f composed with phi. Because in the general case, the range of phi is not contained in the domain of f. So formally, we cannot compose them. But in some sense, this formula is true. Yeah, the spectrum is the essential range, which is not, in general, the essential range of phi is not, it doesn't contain the range. So formally, we cannot compose them, but in some sense, we can do it. So an exercise is to understand what is the composition of f and phi, and to prove this formula. Okay, now in conclusion, I'd like to make a short digression and to recall some basic facts from measure theory. The facts which will be necessary at the next lecture when we discuss the spectral theorem for bounded normal operators. Some facts from measure theory. So suppose that we have a set X and a sigma algebra. Script A is a sigma algebra of subsets of X. And suppose that mu is a complex measure on A, a sigma additive complex measure. So mu is assumed to be complex valued. And I'd like to stress that, in particular, this means that mu is finite. It is complex valued, but it is finite. This is our assumption. We have the following definition. The variation of mu is a non-negative function, denoted like this, on the same sigma algebra. It's not immediate that it is finite, so I write the extended half line here, including plus infinity. And this function is defined as follows. If we take a measurable set A, a set from our sigma algebra, we do the following. We take the supremum of all finite sums of the following form, where the supremum is taken over all partitions of A into finitely many pieces, A1 to AN, from the same sigma algebra. So this is the variation of our measure. And here are some facts on this function. First of all, I claim that the variation is always finite. the variation is finite. And it is a sigma additive positive measure. The second fact is very easy. It is almost immediate from the definition. But the fact that it is finite is not so obvious. But it is still true. It's some little theorem from measure theory. So the sigma additivity of mu implies that the variation is always finite. Okay. From now on, we suppose that X is not just a set, but is a compact Hausdorff topological space. A compact Hausdorff topological space. And we consider the Borel sigma algebra of X. That is the sigma algebra of subsets of X generated by open sets. So we introduce a class of measures that are compatible with the topology. Here we have sigma additive measure, a sigma additive complex measure, mu, on the Borel sigma algebra. Then we say that mu is a Radon measure. Or in other terminologies, mu is regular. If the following condition holds, so roughly the condition is that each Borel set can be approximated by open sets from outside and by compact sets from inside. So for each positive epsilon, there is, and for each Borel set B in X, there exists an open set U containing B, and there exists a compact set K, which is contained in B, such that the variation of U minus K is less than epsilon. So this means that K approximates, K and U both approximate B. So this is K, and this is U, and this is B. Why is this property useful? Well, there are many reasons why it is useful. For example, we have the following proposition. Suppose that mu is a positive Radon measure. A positive finite, well, we always assume that our measure is finite, but I'd like to stress this one once again. A positive finite Radon measure. And let P be a real number greater than or equal to 1. And let's consider the following map. The map from the algebra of the space of continuous functions on X to the big LP space on X with respect to mu. This map just is a kind of inclusion. This map takes each function to each equivalence class. Of the same function. I don't say that this is the inclusion map because we have, in general, this map is not injective, of course. For example, if mu is the Dirac measure, which is concentrated at a single point, then the big LP space is not very big. And so this map is not injective, of course. But on the other hand, for example, if we take the Lebesgue measure on the real line, then this map is, well, not on the real line because X is compact, but the Lebesgue measure on a finite interval on the real line, then this map is injective. And actually, if mu has the property that the measure of each non-empty open set is strictly positive, then this map is injective. But what I claim now is that this map has dense image. This map has dense image. The proof is a simple exercise in general topology. And the hint is to use Morison's lemma. Morison's lemma easily implies that each indicator function of a Borel set can be approximated by continuous functions.
And
X is a compact Hausdorff space. X is as before. X is a compact Hausdorff topological space. And in conclusion, I formulate a classical result, which will be essential in our approach to the spectral theorem. So this set of all complex random measures on X will be denoted by M of X. This is a standard notation. So M of X is the set of all random measures, complex random measures. On X. Well, it's a standard abuse of language. Formally, they are defined on the Borel sigma algebra, but usually we say a random measure on X, meaning that the measure is defined on the Borel sigma algebra. So this is clearly a vector space. The operations are pointwise, and moreover, this is a Banach space. M of X is a Banach space with respect to the following norm. The norm of the measure is defined as follows. We take the variation of mu and we evaluate the variation on the whole space X. This is easily seen to be a norm on M of X. So we have the following fundamental result, which is usually referred to as the Riesz-Markov-Kakutani theorem. But the truth is that this theorem is due to many people. The theorem states that the map from M of X to the dual of C of X, to the dual of the space of continuous functions on X, which takes each random measure mu to the integral with respect to mu, is an isometric isomorphism of Banach spaces. So this classical result will be essential in our approach to the spectral theorem. So we'll use it several times at the next lecture. And that's all for today. Thank you.